Particle P of weight 5 newtons attached to one end of each of two inextensible strings of lengths 30 and 40 centimeters. The under end of the short string is attached to a fixed point A of a rough rod, which is fixed horizontally. A small ring S of weight W newtons is attached to the other end of the longer string and attached on the rod. The system is in equilibrium, so it's not accelerating. The system is in equilibrium with strings taut and AS is 50 centimeters. Horizontally, the force is acting on P in the direction of PS, or otherwise. Find the tension of the longest string. Okay, so find the tension of the longest string. So the idea here is we have this thing can move left or right, but it's not because there's a force of friction holding it that direction, which is balancing everything out. So let's see here. We're going to want to break these things up into components here. So first we have a 3, 4, 5 triangle. We want to find some of these angles here. So TOA. So that's how I solve triangles. And so we know that this side here, so we'll say sine of theta equals opposite over hypotenuse. So opposite is 40, hypotenuse is 50. Therefore, theta will equal, do this, second arc sine of 4 divided by 5. Yep, and that gives us 53. 53 degrees. Probably should make sure I'm in degrees real fast. Mode, yep, I'm in degrees. Second quit. What did I do? Okay, second quit. Now we can tell we know this side here. So 53 plus 90 minus 180, and that should give us 36. I'll call it 37. This will be 37 degrees right there. So now we can also find this triangle right here. So that's 90. So that's 53, 90. Looks like that'll be the same. So this will be 37, and then this will be 53 degrees. Okay, and I think that's all I need to know for this portion. So now we're trying to find the tension on this wire right here. So what we're going to do is we're going to have to balance the X and Y tensions. So I'm going to start by writing things out a little bit. So we know that there's a force gravity on P, force gravity P. So force gravity P is acting downward, and that will equal the sum of the upward forces. So that will be tension of the 30 string, it's this one right there, in the Y direction, plus tension of the 40 string in the Y direction. So that's going to be, so we have this angle right here. So that would be tension of 30 times sine of 53. So this is just geometry. So tension of 30 times sine of 53. So what I'm looking at is, if this is a vector like this, this will be the tension. Get a different color so it's more obvious. Like this. I can then break that up into an X component and a Y component. So if I look at it this way, this portion right here will be the sine. Clear that up real quick. This will be 53. This will be 37. Okay. And then we're going to add to that the tension of the 40 times the sine of 37. So sine of 37, here's the 37. Sine of 37 would be this vertical line as well. Okay, so that's going to be the vertical lines. Now we know that the horizontal components are going to oppose each other. So we have tension 40 pulling this direction. This will be tension 40x. This will be tension 30x. So 30 just refers to this string right here, and x refers to the x direction. So that will be tension 30 cosine of 53, 53 plus tension 40 cosine of 37. See if I got that right. So here, cosine is up here. Yep, I think it probably is. And so now we have two equations, two unknowns, and we can solve it. Oh, we also know that this equals 0 because they cancel each other out. And this is going to be mass of P times gravity, where P is the particle that's being held. Okay? So now, rearranging this and solving for, we want tension 40, so I'm going to solve for tension 30, and then plug that into the above equation. And so, let's see, do we know the mass of P? We do. So then, rearranging this, we have tension 30. One thing I should not forget here is I'm going to say that there's a negative in here. Really, these angles should all be measured from the same start, but they're not. I want to have the negative sign in there to show that one tension is going to the left, other tension is going to the right, that they are opposing each other. So tension 30 equals tension 40 cosine 37 over cosine of 53. And the idea is you move one of the tensions over, that negative sign then disappears. So we can calculate this out a little bit, depending on how exact you want to be in life. So cosine of 37 divided by cosine of 53. And that gives us 1.327. 1.327 times tension 40. Okay. So now we can take this equation right here, and we know that on the left side, mass times gravity of particle P, they give us is 5 newtons. So I'm just going to write that as 5 and let the newtons be assumed. So what we can do then is plug in this for T30. So we have 1.327 T40 times sine of 53, right up there, plus T40 sine of 37 plus T40 sine of 37 equals 5. Okay? So T40 equals, let's see here if I can do this, 5 over, factored out, 1.327 times, down a little bit, sine of 53 plus sine of 37. Okay? So going to the calculator, so we have 1.327 times sine of 53 plus sine of 37. Then 5 divided by second answer. And that gives us 3. So T40 equals 3, almost exactly, newtons. And it might actually be exactly 3. It might have something to do with the fact that this is a 3, 4, 5 triangle. Not entirely sure. And that the particle weight is 5. Probably something there. I don't know. Okay, so tension in T40 is 3. Okay, sounds good. Next step here then is to find the magnitude of the frictional force acting on S. This little ring that we were talking about with friction. So the force of friction is going to be equal to this T. So we have T40x pulling this direction. So force friction is going to be the same but going in the opposite direction just to offset it. So we're trying to find the magnitude of the frictional force. So frictional force equals T40 in the x direction, which will be T40, which is 3, times the angle that it's at. So we have cosine of 37. because that's 37 degrees. Cosine will then give us this value of it. Yep, I'm good with that. And so I'll have times cosine 37. We'll get about 2.4. 2.4 newtons. Find the magnitude of the frictional force acting on S. Yep. And we want magnitude so we don't have to worry about the sign, but the sign would actually be negative because it'd be going opposite direction of tension 40 in the x direction. So not too bad. Given that the coefficient of friction between S and the rod is 0.75, and the S in the limiting equilibrium is in limiting equilibrium, meaning that it's just barely holding on, find the value of W, W being weight. So if we have force friction, that's going to be some coefficient of friction. I'm going to say static, that's not moving, as opposed to kinetic, times the normal force. Normal force in this case is going to be mass times gravity, which will be the same as weight. And so the force of friction is 2.4. So we have, rearranging this, we have force of friction divided by mu static. So this would be 2.4 over, I think it was 0.75? 0.75. Oh, 0.75. If I was better, I could do that in my head, but I'm not. Maybe 3.2? Let's try. So divided by 0.75, and we get 3.2. 3.2 newtons will be the weight, or the force due to gravity, of ring S. So I think that's pretty much solved. To kind of backtrack what we did here, we were given a particle that was being suspended by two strings. We had to break down the components of the tension of the strings into x and y components. That gave us two equations. We then solved those two equations. You have two equations, two unknowns, then you can solve it. That's what we did. And we didn't really know where we were going from the start. We just kind of started working our way through, and eventually we got enough answers. One thing to be careful about is making sure your signs make sense. And then when you have two forces opposing each other, your signs are they have to be opposite. If you have two forces that are making each other stronger, then you should add them together. And then we just kind of worked our way through. So I hope that helped how I would approach this problem. See you next time.